So in this video we're going to talk about signals again, but from a very different viewpoint. In all the previous videos when we talked about circuits, we discovered that if we could express a signal as a superposition of complex exponentials, in particular I'm thinking of the sinusoid, then solving the circuit was easy. The complex exponential was a natural input to study the circuit's behavior with. However, sinusoids by themselves are pretty limiting. We need to talk about more general signals. But still would like to express a signal as a superposition of complex exponentials. Can we do that? And the answer is yes. So we're going to begin by talking about periodic signals, something called the Fourier Series. And what we're going to discover, which is a very interesting point, is that you can define a signal as a function in time or as a function of frequency, and we can get between the two representations of exactly the same quantity using the Fourier series. And so we're going to start talking about signals in what we call domains. We can talk about them as functions of time, or we can talk about them as functions of frequency, whichever seems to be most convenient. But to get started, we need to define a Fourier series and understand it a little bit. So, this is the Fourier series for a periodic signal. This is very important. It's periodic with period t. And Fourier claimed at the beginning of the 19th century that you could express a periodic signal as a superposition of complex exponentials, the frequency of which was k over t. So this is the kth harmonic of the fundamental frequency 1 over t. So the fundamental is the first harmonic, then there's the second, the third, and the fourth. You notice k here goes negative, so we actually talk about the -1 harmonic, the -2 harmonic, etc. And we'll see how to handle that in just a second. The coefficients of this expansion are called the Fourier coefficients. So what Fourier claimed is that if you give me a time signal, there are some coefficients here, c sub k, that allow me to express this signal as a weighted superposition of complex exponentials. Well, the question is, what are those ck's? How do you find them? Well, we're going to use properties of the complex exponential here of what are called harmonically related complex exponentials is extremely important. And it goes by the technical term orthogonality. So I want to consider this integral between a complex exponential having a harmonic number of k and one that has a harmonic number of -L. Well, let's do this integral. So we have 1 over t, and we have the integral. Now I'm going to merge the two exponentials in the exponents. Okay, and do this integral is rather easy. We just have to bring down the quantity multiplying t, put that in the denominator, and the integral gives us back the exponential, of course, so we get 1 over t, 1 over j 2 pi k minus L t times the same thing. Except now it's evaluated 0 to t. Well, what do we get when we evaluate it at the upper limit here? Well, the t is capital T, so these cancel. And what you're left with is e to the plus j 2 pi times k minus L. And evaluating at 0 gives us 1, of course. Well, What is e to the j2 pi times an integer for any integer? Well, I hope you said that the answer is 1. So this term turns out to always be 1 for any value of k and l. The difference between two integers is another integer, so e to the j2 pi an integer has got to be 1. So it looks like we get 0 for an answer, 1 minus 1 here. That seems to be kind of odd, until we realize over here in the denominator that we have a k minus l. So when k equals l, the numerator here, given by this term, is 1. Well, the denominator is also 0. So we have a problem. Numerator is 0, denominator is 0. How do we figure this out? Well, let's go back and look at the original integral when k equals L. Well, rewriting it just like I did before, k equals L, this is 0, which makes this 1. And so the integral gets very easy. You get the integral of 1 from 0 to t, that's capital T, divide by capital T, you get 1. So that's why this is true. As long as k does not equal L, then you get this integral is 0, but when k and L agree, you get 1. Okay, well, that's a very important property that's very useful. So suppose I take my expression for s of t, right? And I'm going to multiply both sides now by that. And integrate. Well, we know over here what happens. Over here, the only time you get anything is when k equals L. So what happens, all the terms in this sum disappear except for the Lth, whatever L is. And that leaves us with the following result, that the C sub L term is equal to the original signal times a complex exponential having a frequency of minus L over T, integrate and divide by capital T. So the idea is, in order for this to be true, the C sub K's, the C sub L's, have to be given by this, or else it cannot be true. Well, this is a way that, given the periodic signal as a function of time, I can find its kth Fourier coefficient. So there's an equivalence here, which is an important thing to realize. So, given the signal, I can find the C sub k's by using this expression. And given the C sub k's, I can find the signal by using this expression. So I can go back and forth, as the arrows suggest here, and between the time domain, expression of the signal as a function of time, and the frequency domain, the expression of the signal as a function here of harmonic index, where as a function of k, you have to give me the C sub k's, and the complex exponentials are understood because we know what the period t is. This is going to be a very important concept as we go through, an important result for us right now because of the superposition property. Well, let's figure out the Fourier series for some simple waveforms. So here we have our sine wave, and I've given it a phase this time to make it a bit more general. So the period is 1 over the frequency. So this is the fundamental frequency, is just f0. And I could do the integral, but I want to illustrate something by